so solutions and their concentrations. So a solution is a homogeneous mixture, which means if you look at it, you will only see one phase. So you'll just see one thing, not many different things put together. So it can be a solid, like an alloy. For example, if you have any jewelry like gold or silver, it's probably a mixture of a whole bunch of metals. It can be a gas, like the air. It's a mixture of nitrogen gas, oxygen gas, and so on. Or it can be a liquid, like apple juice. So for this unit, we're going to be focusing on mixtures that are liquids. More specifically, most of the solutions we'll be looking at are aqueous solutions. So aqueous solutions are any solutions where water is the solvent. A solvent dissolves a solute and it's present in a larger amount. So if you have a mixture, an aqueous mixture, the solvent is always going to be water. The solute dissolves in a solvent and it's present in smaller amounts. So for example, if I have salt water, salt is going to be the solute and solvent is going to be water. So an important definition to keep in mind is solubility. So the solubility is just the maximum amount of a solute that can dissolve in a given volume of solvent at a specific temperature. It's important that we note that it's at a specific temperature because solubility is temperature dependent. Usually as you increase the temperature, you'll increase the solubility of a compound. So there are generally three different types of solutions. So first is an unsaturated solution. So an unsaturated solution means you have a solution, you dissolved a bit of solute in there, so for example some sugar. You dissolved a little bit of sugar in there, but it's unsaturated, which means you can still dissolve more sugar in there. It hasn't reached its maximum solubility yet. A saturated solution means you can't dissolve any more sugar in it. It means if you have a glass of sugar water and you try to add more sugar, the sugar will just fall down to the bottom and no matter how much you mix it, it won't dissolve any further. The third case is a supersaturated solution. Sometimes you can actually get a solution that is above its solubility. Very rarely though. So the easiest way to do this is to mix a whole bunch of sugar in water, like I said before. Make sure that it's saturated, then keep adding sugar. If you heat it up, remember temperature is directly proportional to solubility, so if you increase the temperature, you'll increase the solubility. So that amount of sugar that was at the bottom that didn't dissolve at first will dissolve when you increase the temperature. And then if you bring down the temperature slowly, you'll have the sugar dissolved still, and any shock to that solution will cause the sugar to crystallize instantly. Something like this is used when you're trying to make, say, rock candy. Now the rate of dissolving is dependent on three things. The first is temperature. So as you increase the temperature, a solute will dissolve faster. Remember, it's the rate, not the amount that we're talking about now. Agitation, which means that if you mix a solution, the solute that you're adding will also dissolve faster. If you have, for example, when you're making tea and you're putting in sugar into that, you probably want to dissolve it quickly by stirring it instead of just leaving it there. The third is the size of the solute. If you want something to dissolve faster, you use smaller particles. So, for example, instead of getting chunks of salt to try to dissolve it in water, just get the table salt and it'll dissolve a lot faster. So next I want to talk about the solubility of solids and gases in an aqueous solution. Just picture the kinetic molecular theory. If you have a temperature increase and you're trying to dissolve a solid, that solid will dissolve faster and will dissolve more because there are more movements between the water and the solid. However, if you have a gas and you're trying to dissolve it, the solubility is actually going to go down because the gas will be moving faster, and as soon as it moves and hits the surface of the water, the gas will now leave the solution, and it's very hard to get it back in. Now if we take a look at the effect of a pressure increase, if you increase the pressure on a solid in water, so an aqueous solution with solid as the solute, there will be no effect because it's a solid and you can't really compress a solid. But if you have gas dissolved in water, the solubility will increase if you increase the pressure because that's forcing the gas back in. So I drew a little diagram here to represent the kinetic molecular theory. So everything below this line over here is a solution with this red particle representing the gas dissolved in it. If you increase the temperature, the gas molecules will start moving faster in the solution, and as soon as it hits the surface of the water, it's now free to escape. It's very hard to get it back in though. If you increase the pressure though, that's where you can get it back in. Increasing the pressure is just imagine it as squeezing down on these gas particles. So when they're up here, you can squeeze down on them and force them back into the solution to increase the solubility. So now let's move on to concentration. So concentration is just a way of saying how much solute is in the solution. So there are a few different ways, I haven't listed them all here, but these are some of them, of determining concentration. So the first is mass over volume. So the concentration is just the mass of the solute over the total volume. The next is volume over volume, which is just the volume of the solute over the total volume. In this case, it's important to add the volume of the solute and the solvent to get your total volume. The third is mass over mass, which is just the mass of the solute over the total mass. Over here also it's important to add the mass of the solute and the solvent. Most importantly, and the one we're going to use most, is the molar concentration. So the molar concentration is just the moles of solute divided by the volume of your solution. So I have an example here of determining how many moles of KCl are in 2.35 liters of a 0.8 moles per liter solution. So this is the concentration right here, moles per liter. So this is our equation, and just putting in the values, we're looking for the number of moles. Simple rearrangement gives us 0.8 times 2.35. So in the end, we get 1.88 moles of KCl. So lastly, let's talk about diluting solutions. So the only equation you guys really have to know is C1V1 equals C2V2. So let's do an example. So what is the concentration of sodium phosphate if 1.56 liters of a 2.49 molar solution is diluted with 2 liters of water? So C1V1 equals C2V2. So here I have our initial concentration, 2.49, our initial volume, C2. Our final volume, remember that our final volume is going to be our initial volume plus the amount of water that we're adding. So it's not just 2 liters of water, it's 2 liters of water plus the volume of original solution that I have. So simple arrangement gets us this. Note that the liters cancel out, and we should end up with 1.0 moles per liter is our final concentration. It's important to realize that if you're diluting, your final concentration should be less than your original concentration. So if you get a final concentration higher than your original concentration, you know you must have done something wrong, so go back and check.